the exida webinar, FMEDA tips and techniques. In the last 30 years, since we invented the FMEDA techniques, we have been able to gather up a lot of experience. And mostly the FMEDAs have gone pretty smoothly based on our original design concepts. But sometimes you hit issues that just seem messy, complicated. Today, we're going to talk about some of those issues and explain how we have worked hard to come up with ways to keep our FMEAs accurate, but effective, but streamlined, so they can be done in a practical amount of time. This is webinar number 6 from the exida Spring 2023 FMEDA webinar series. I hope you've been able to see all of our webinars. They are all recorded online. My name is Bill Goebel. I work for exida. We are all quite proud that our company has grown into a global supplier of top technical information. Professionals around the world turn to us for guidance, tools, and certification. FMEDA, that stands for Failure Modes, Effects, and Diagnostic Analysis. It's a quantitative analysis technique, bottom-up inductive approach necessary to generate detailed reliability metrics for functional safety. It's also valuable for general reliability and availability calculations, as well as perhaps warranty data. The concept behind the FMEDA is that we have a single device or a subsystem composed of a series internal reliability organization. We generate metrics for this single device, a device without redundancy. Then we use those metrics in a systems level probability model with a Markov or a fault tree. Markov, if it's a repairable system, online repairable, and fault tree if it's not, are my preferences. And the process goes pretty smoothly. One of the inputs you need to do a good functional FMEDA is a hardware architecture drawing with failure mode descriptions of each block. Given a block and a failure mode, you classify that according to the functional safety failure modes, safe, dangerous, enunciation, no effect, not safety related, the functional safety normal failure mode categories. For example, on the left side of your screen, you see a power supply block. And one of the failure modes of the power supply block is no output. Power went to 0. And in this particular example, that has been classified as a dangerous fault because this particular device hasn't energized to trip output. And without the power supply, we cannot execute the safety function. Well, when you have a list of those blocks, we can enter the components for the block. You call up or generate the failure modes for the components, and you map them into the failure modes of the block. And this way, when we go, if we need to change the design or update, we can work with block failure modes, not with long lists of components. It's a technique we call failure mode FMEDA, and it's really been a strong advantage to work this way. But sometimes things don't go smoothly. And questions come up like, do the block failure modes change with mitigation response? In other words, automatic diagnostics and the actions taken. What's the minimum level of diagnostic enunciation required to give credit for diagnostics? What about redundant components on the circuit board? How do we give credit for that, or do we have to break it up into multiple subsystems and build a fault tree? How do you give credit for multiple automatic diagnostics? Well, we're going to talk about these issues and more today during our webinar. Let's take a look at automatic diagnostic response. Automatic diagnostics are a great thing. Many think it's the future of functional safety. The main way to achieve functional safety is with automatic diagnostics, in the view of many. Well, what happens when the automatic diagnostic detects a failure inside of a device? Well, a common solution is to shut down the process. In other words, take the output of the device to its safe state. Another solution might be to reset the microprocessor and continue running if startup diagnostics are successful. But you can't do that forever. There's probably some limit on how long you can do that. Like a common choice might be 3 times. Then you have to go to one of the other choices. And third choice, enunciate the failure to request operational response. In other words, I failed. Come and fix me. Number one is the most common solution. And a lot of people probably do this, make this choice without really thinking. One famous example was the U.S. Space Shuttle engine controller. The engine controller detected an internal failure, a microcomputer controller. It was managing the engine and it detected a failure inside of itself and decided to shut down the engine to save it from damage because it was no longer capable of providing protection. Then someone realized a much bigger consequence is total destruction of the vehicle if the engine did shut down unnecessarily. So obviously that shutdown decision was changed. In any automatic diagnostic, the choice, 1, 2, or 3, must be made by the designers, and whomever is doing the FMEDA analysis must know that choice. And so that's often something that is optionally, that information is usually part of every FMEDA tool. And in this case, a power supply low voltage monitor detected the 0 volt condition, which we're concerned with. And the designers chose to enunciate the failure. Well, if the choice is number 1, automatic shutdown, how does that impact the results of the FMEDA? If you think about it a minute, you'll see the answer. Any failure, whether it's classified as dangerous or enunciation which is a diagnostic failure, is now converted into a safe failure. So your FMEDA results should not show DDs or ADs. All of those should be added together and called safe detected. Another issue that's come up is what are the minimum requirements for an automatic diagnostic? Well, let's say a choice is made to enunciate the failure and get the repair team to come and fix the problem. Well, one product came in for an FMEDA as part of our certification group, and we asked We didn't see any information on the action taken when a component failed. So we ask, what do you do? Oh, we enunciate the failure. How do you do that? A light flashes on the outside of the box. A light flashes. Oh, aren't these designed to be put inside a cabinet? Yes. So you expect a person to frequently come and check open the cabinet door and see if the light is flashing. Yes. No, it's not going to work. The probability of human error, the probability, especially in low safety culture installations, is really high. And so we've chosen not to give any diagnostic enunciation credit for anything that doesn't have an automatic electronic signaling back to the maintenance station or automatically shuts down. In those cases, unfortunately, everything that you had previously marked safe detected or dangerous detected or even enunciation detected, they all turn into undetected. All right, might be conservative, but we're talking automatic diagnostics, not manual testing and manual inspection of the test. There were some times when we were doing some FMEDAs, even early on, where we discovered the functional failure modes could not logically be mapped into safe versus dangerous. Imagine a sensor device with an analog output. Functional failure modes, functional failure modes include the output going high, the output saturates low or drifting high or low. And then someone asked, well, doesn't the category safe versus dangerous depend on whether this product is used in a high trip or a low trip application? And the answer is yes, it does. Imagine a high trip. A failure where the output saturated high would be fail safe. But if it's a high trip and the output goes low and will not reflect the proper signal, that's a fail danger. And so in this case, we learned pretty early on that sometimes we have to publish these functional failure modes like high or low instead of just safe, dangerous, enunciation, and no effect. Then sometimes we saw redundant components on a circuit board. It's not a single repairable unit. For example, consider the diode in this flasher power supply. This is a energized to trip output. A flashing device, an alarm annunciation, flashes a bright light to warn people of danger. That's the safety function. That's energized to trip, because you have to have energy to make the light. Well, the designer was going through the failure modes of the components in an FMEDA and realized that if that diode in the schematic in your upper right side fails open circuit, the output will go to 0 volts. That's fail danger. And so the designer focused on this particular component at the time, thought, wow, we're just going to put in a second diode. Then, even if one diode goes open circuit, the other will still supply the power. Isn't that a wonderful design change? Well, now if either diode fails short, we lose our reverse polarity protection, which is why the diode's there in the first place. But maybe that's a reasonable trade-off. Let's take a look at what happens to the dangerous failure rate. Maybe, you don't have to take the dangerous failure rate to 0. An easy way to model a redundant component is to recognize the impact of common cause failures. Common cause probabilities are higher when you have identical components exposed to the same stress. Two components on the same circuit board are highly likely to be exposed to the exact same stress. So we realized that we could take those two diodes and replace it with a line on the FMEDA, which we'll call redundant diode. Now, the common cause failure rate at a 20% beta model, which is probably a wee bit conservative, would lower the dangerous failure rates of this component from 1.4 fits to 0.28 fits. So we dropped a little over 1 fit. As I recall, the total dangerous failure rate on this result was about 170 fits. Dropping it by 1 is probably not worth it. Probably not worth the cost, and it's not worth the increase in losing the reverse polarity protection. But that is a design decision the team can make. As far as we're concerned, for the FMEDA analyst, we can do this without separating this design into multiple subsystems and creating a fault tree. Common cause dominates. What if there are more than one automatic diagnostics for any given failure mode? Once, one of our customers came in with an FMEDA where they really wanted to detect this particular problem. This is a nasty, dangerous condition. So they put in two diagnostics. The first had a coverage factor of 90%. The second had a 99%. The argument was, look, let's say the 99% diagnostic detects 99% of the failures, leaving 1%, and the second diagnostic detects 0.9% for a total of 99.9% diagnostic coverage. With that, my product passes SIL 3. And we were looking at it and said, something doesn't feel right with this. What if both diagnostics detect the same component failures? Sorry, you don't get any credit for the 90%. The rule is use the higher of the two and stop. Very disappointing to the customer, and perhaps it's a wee bit conservative, yes, but but that's all right without a lot of detailed justification. You could possibly claim more than 99%, but each component failure must be examined to make certain that if the 99%, first to make certain that there are no common components detected by both diagnostics. And every time, we've only done this a couple times because it's expensive. It takes hours and hours of time. And in both cases, it kind of turned out that only the first diagnostic really worked. Also, another issue came up over the years, and you have to be careful about your definitions of failure modes. This power supply circuit should have transient voltage protection, so a transient suppressor has been added to the input. And now we have to add this to our FMEDA. What is the failure mode of the transistor suppressor open circuit? Well, if that component fails open circuit, we would certainly lose our transient suppression, and other components downstream would be subject to higher levels of electrical stress And then we read the definition in 61508-2010, Part B, which says decreases the probability that the safety function operates correctly. You know, this looks like this we could argue this loss of a transient suppressor would cause a decrease in the probability that the safety function works correctly. So should we categorize this, the failure rate for this open circuit, in fail danger? Well, let's ask, does the safety function still work? Yes, it does. It works perfectly. Well, then how in the world could you ever classify this as fail danger? It sure doesn't look like a good idea. You might think you're being conservative, but that's way too conservative when you realize that two components have to fail. If you have a 10 to the minus 8 failure rate for the open circuit transient suppressor and a 10 to the minus 8 for another component downstream, if A and B fail, you multiply basic rules of probability. 10 to the minus 16. Now, come on, we don't have nearly enough decimal points in our numbers to account for that. So it feels like this doesn't make any sense classifying it as dangerous. A level of protection has been lost, but if you have a component database based on field failure analysis, one could argue, and I will argue, that the failure rates of the internal components already reflect the impact of this. The other internal components already display the impact of this, because if you have a population of devices out in the field, the transient voltage suppressor did go open circuit in some of them. And therefore, we are going to classify this as no effect, not dangerous. One of the other problems that we saw a couple times is not good. A problem many in some fields call analysis paralysis. FMEDAs are based on average failure rates and average design strength. And in certain cases, a good component reliability database will give you a selection of design stress, which does impact both failure rates and useful life. But if you wonder, is this good enough? What if you think your design is much better than average? Well, you can dig in and you can do a lot of measurements, and you can attempt to use stress strength models to justify a lower failure rate. It can be done. An FMEDA came in from a customer. It looked pretty well done, although some of the failure rates looked a bit low. And we say, how do you justify this? And by the way, how long did your FMEDA take? And he said, 3 months, 200 parts. 3 months? This should have taken 2 weeks, maybe a week. He spent an extra, what's that for? He spent an extra 10 weeks. Was that time and the cost of that justified? Probably not. It can be done, but make sure if you're going to dig deeper, it's completely justified. All of these tips and techniques work depending on whether you're using your own spreadsheet or a commercial tool available on the market. And all of these techniques can be applied to either method. The tools are generally much simpler to use, especially if they have a good built-in component reliability database. So in conclusion, FMEDA analysis, and I know that it can be is good. I know it can be time consuming, and therefore analysts and their management must identify ways to keep it more efficient and streamlined without significantly impacting the results. And if it does impact the results, we expect it to be a bit conservative and generate higher failure rates. Many errors can be made in an FMEDA without considering the impact of mitigations, like automatic diagnostics. You have to make certain you understand the actions taken when a component failure is detected. If multiple mitigations are chosen, we generally assume immediately that they do not detect different failures, and therefore credit is given only to the best of multiple mitigations. In most cases, it's rare that a multiple mitigation will give you any benefit over a single. Pick the mitigation that gives you the best diagnostic coverage. The FMEDA is done for an architecture design block, which is internally a series reliability system. Any component fails, block fails. Block redundancy is modeled using the FMEDA results in a Markov model or a fault tree. I thank you very much for your time and attention. Just a note that Exida has a suite of software called OEMX, and one of the tools in that suite is an FMEDA tool called FMEDAX. I thank you very much for your time. I hope you found the information valuable. I hope if you're doing your own FMEDAs, they will go faster and quicker. If you have any questions, please don't hesitate to refer to the white papers on our website. We have a lot of white papers on FMEDA, including some of the early papers from the time when we invented it. Thank you very much. Take care. Bye-bye.